says we are work on geometry and physics, so we try to put together physics and mathematics in different ways. And one of the local families, the De La Pietras, like to fund a sets of lectures where we can have very distinguished researchers talking to us, but also they insist that the researchers talk to the high school students. That could serve as inspiration, maybe inspired to do something after you get this talk. This might actually guide into your career, or it's just a good way of getting information about the type of activities that we do. Today, I think that Professor Charles Kane is one of the examples of someone who really has united, in a certain extent, in his work, mathematics and physics. He's somehow following under the trail set by Dirac, Young, and a few, Chern, Simons. So these are names that perhaps do not sound much to you, but if you go into physics and mathematics, in very few years' time, you will realize that these are really pinnacles for some of the great pioneers in our field. So rather than telling you about all the honors and prizes, of course, he just got the Fundamental Physics Prize, which is one of the most distinguished recent prizes that have been made. He might actually be visiting some of these northern countries in Europe soon. We don't know when. But in any case, rather than boring you with this, you can go to the Wikipedia pages or his webpage and find out all the things about his biography. So he will be telling you today about the emergence of topological quantum matter. So enjoy.
Okay, well, so thank you very much, Luis. So look, it's really this is really fun for me to get in front of a bunch of young people, so I want to try to tell you a little bit just about how cool physics really is. I mean, it's really amazing, and in particular, I'm going to talk about let's see if I use that. Yeah. Topological quantum matter. Now that's a bit of a mouthful, but what it has to do with in what I'm going to be talking about is the electronic properties of matter. Okay, and matter can arrange itself in the most ingenious ways. Okay, and so in order to sort of set the stage for this, so electronic properties of matter. This is a physics that you study in a high school physics course or in a college physics course. In fact, I actually, this last semester at the University of Pennsylvania, I was teaching freshman physics, freshman electromagnetism. And I have to say, this is the most fun course to teach, of all the courses that I teach. It's really a beautiful subject. And I hope you get an opportunity to learn about electricity and magnetism. So what I'm going to do is I want to go back to the beginning, the very beginning of electricity and magnetism. Give you a little history lesson. Because back at the very beginning of electricity and magnetism is Benjamin Franklin. Okay, so I don't know about here, I come from Philadelphia, and in Philadelphia, Ben Franklin is a big deal, okay? Everything is named after him in Philadelphia. And so, of course, he's most famous because, of course, he was one of the founding fathers of the United States of America. He was a famous statesman, diplomat. But he was a real Renaissance man. So in addition to being a statesman, he was a very distinguished scientist. And then, of course, I come from the University of Pennsylvania, and he was also, maybe I should put this at the top of the list. He was also the founder of my university. Okay, and so we talk about Ben Franklin a lot at Penn. But in any case, as a scientist, what Franklin was famous for was he did the first systematic observations of the phenomenon of electricity. So electricity, this is the stuff that lightning bolts are made out of. Okay, it's also the stuff that makes your socks stick together when you take them out of the dryer. Okay, so that's electricity. Okay, and so what Ben Franklin is famous for is he did these famous experiments where he went out into a lightning storm and flew a kite. Now, don't do this. That's not a good idea. Okay, it's amazing that he didn't kill himself doing this. But in doing so, he discovered something very fundamental about matter, which is one of the attributes that matter can have is what we call electric charge. Okay, and it's electric charges. So what Franklin discovered is that electric charges can be positive, and they can be negative. Okay, like electric charges push each other apart, and opposite electric charges attract each other. So this is something that Ben Franklin realized, and this is sort of a fundamental aspect of the universe that we live in. Okay, and he discovered another fundamental thing, which is that there are basically two different kinds of materials, two different kinds of pieces of stuff. Okay, there are materials that we call conductors, in which electric charge can flow, sort of the way that water can flow through a pipe. Okay, and there are also materials called insulators that don't allow electric charge to flow. Okay, and so this was sort of a fundamental property of matter that Ben Franklin sort of recognized the importance of. But so this is something that's very deep and fundamental. But Ben Franklin was also a very practical man, and so he realized that having this fundamental discovery allowed him to do something that is really useful. Okay, and so in fact, this discovery allowed him to invent one of the most important technological discoveries of his day, which is the lightning rod. Now, so the lightning rod, of course, is the way you can keep your house from burning down in a lightning storm by having an electrical conductor that sort of shorts the electricity so it goes down into the ground and not through your house. Okay, and so in addition to being incredibly fundamental, this is incredibly useful. Okay, and so to me, Ben Franklin really sort of epitomizes what is good about science. Okay, it's both deep, beautiful, and fundamental, but it's also very useful. Okay, and so this has really been the story about how our understanding what it can do, how that understanding has evolved over the last couple of centuries. Okay, and boy, what a ride we've been on over the last 250 years. Because now, fast forward to the present day, and we have electronic materials that can do the most amazing things. Okay, so everybody has a computer, a powerful computer in their pocket. Okay, and our ability to do that, to master electronic materials in order to be able to do things like this, is a direct consequence of the understanding of the electronic structure of matter that has evolved over the last 250 years. Okay, and so what I want to try to tell you about today is that this understanding we have of the electronic properties of matter is continuing to develop. Okay, we're continuing to learn new things, and these discoveries of what I'm going to call new electronic phases of matter, they can enable new kinds of technologies that are even kind of hard to think about. Okay, and I want to try to explain to you some of these things. Okay, and so what I want to try to get across to you is I want to get both sides across, both the fundamental and the beautiful aspect of this, as well as what you might be able to do with it. Okay, and so I want to tell you about electronic phases of matter. So let me just tell you what a phase of matter is. So the thing that's really interesting is that matter is made out of relatively simple building blocks. Okay. They're atoms and electrons. But what's amazing is that when you have lots of these building blocks, you can put them together and they can do amazing things. And so one of the things they can do is they can form different phases. The most familiar phases are maybe water has a liquid phase, liquid water, and then it freezes. It has a solid phase, which is ice. Okay, and so those are two different phases, and they behave completely differently, even though they're made out of the same building blocks. Okay, and these are examples of phases of matter. Another example, if I want to think about the electronic properties of matter, is again this distinction between a conductor, like a copper wire, and an insulator, like the rubber that you might surround a copper wire. Okay, and so these are also two different electronic phases of matter. Okay, and so I want to try to explain to you some new phases of matter that are going to be something which are really kind of cool. And in order to do that, I want to sort of come to the beginning and think about the fundamental building blocks of matter, what matter is made out of. And so this is a physics which sort of came into focus in the early part of the 20th century, in the early, around 1900, the early part of the 20th century. And so at that time, we came to understand that matter is made out of fundamental particles, okay? And those fundamental particles, the most important ones are basically the electron, the proton, and the neutron. And the important thing here is that the electron and the proton are charged. Okay, the proton has a positive charge, and the electron has a negative charge. Actually, there's kind of a funny story here. So Benjamin Franklin, he discovered charge, and so he was the guy who got to decide which one was the positive and which one was the negative. Okay, and now of course he didn't know about electrons. Okay, and so he chose which was the positive and which is the negative. And so it turns out, that given his choice, the electron has the negative charge. And so this choice that Franklin made was the most unfortunate choice that he could have possibly made. Okay, because this minus for the electron is the source of endless confusion for students at your stage trying to solve problems in electricity and magnetism, because electric currents, are due to the flow of electrons, and the electric current is in the opposite direction the charges are moving. Okay, and this minus sign, so we're stuck with Benjamin Franklin's minus sign. We can't, he got protons and neutrons. They arrange themselves into atoms. Okay, and you can sort of think of an atom as like a little mini solar system, okay, where the electrons are sort of like the planets orbiting around the protons and the neutrons, which form the nucleus, and they're sort of like the sun. Okay, and this picture of a little solar system, there's a sense in which that's kind of right. Okay, but you see, there's an important point that I want to make is that the charge of an electron and the charge of the proton is precisely quantized. Every electron has exactly the same charge. Okay, and it's impossible to cut an electron in half. You can't have any charge that's any smaller than the charge of the electron. Okay, so in this sense, we say that electric charge is quantized. Okay, so you can't have half an electron. Okay, and so that's a fundamental aspect of matter. Okay, now so we have this solar system picture for an atom. Okay, but it turns out this picture is incomplete. Okay, and so this is another one of the dramatic discoveries that was made in the early part of the 20th century, which is quantum mechanics. Okay, and now quantum mechanics is a little bit more advanced physics, but so I'm not going to teach you quantum mechanics in this hour. Okay, but what I can do is I can tell you what the consequence of quantum mechanics is for atoms, and basically what quantum mechanics tells you is that in an atom, the ways that electrons can sit in an atom is very sort of constrained. So in an atom, the electrons can only sit inside, they can occupy discrete quantized energy levels. And what this means is that in an atom, the electrons are it's like they're snapped into place. They're locked into place, and there's no play. They can't wiggle around. I mean, so it's almost as if the electrons are snapped in the way you snap Legos together. Okay, and they're stuck, and everything is fixed. In order to get the atoms to, in order to get the electrons to do anything, then you have to give it a finite kick. Okay, you have to give it a finite amount of energy in order to get the electrons to do anything. So there's a barrier to having the electrons do anything. Okay, and so this is the sort of fundamental aspect that quantum mechanics gives us in talking about atoms. Okay, and the word that we associate with this sort of locking of the electrons into place is we say that there's an energy gap in these atomic orbitals. So it takes a finite amount of energy in order to get the electrons to do anything. So this existence of an energy gap in an atom actually allows us to understand the most basic electronic state of matter, which is the insulating state. Okay. Now I told you, I teach freshmen electromagnetism, and I tell them about conductors and insulators. Okay. And so the word we say for an insulator, what an insulator is it's a material where the electrons are basically stuck to the atoms. Okay. And then they can't, they're stuck at home. They can't go anywhere. And so that's what an insulator is. Whereas a conductor has sort of free electrons that can move around. Okay. Now, but the thing is that this fact that the electrons are stuck in an insulator, it's really a consequence of these two features that I told you before. The fact that electric charge is indivisible. I can't split an electron into tiny bits and have it flow. And also the quantization that locks the electrons in place. So in this insulator, which is just a bunch of atoms where the electrons are locked in place, the electrons can't do anything. They're stuck. It's like, and there's a sense in which this insulating state, it's kind of the most boring state of matter. The electrons, they don't do anything. They just sit at home. But it's a little bit more interesting than that, because there is one thing you can do in an insulator, which is you can add an electron. It has already, overcome this gap, and it can move around. You see, it can hop from one site to another, and so this added electron can flow around. Okay, and so if you add electrons to an insulator, it becomes an electrical conductor. Okay, and this electron, is an excitation of an insulator, and it has an exact charge of, according to Benjamin Franklin, minus E. Okay, but there's something else that you can do in an insulator, which, it makes sense that, so the matter is made out of the electrons, so it makes sense that electrons can move around. But there's something else that can happen in an insulator, which is a little bit less simple. Okay, which is, instead of adding an electron, I can take one out. Okay, so if I take an electron out, then I have a missing electron, and so this is going to have a charge also. But since the electrons have a negative charge, I took one out. It's like I'm subtracting a charge minus E. So this hole, that's what we call it, a missing electron, has a charge of plus E. Okay? Now, this hole is like a particle too. It can move around just the same way the electrons move around. Watch. So all that has to happen is that one electron has to move over, take its place, and then the hole is moved over. It can move over again and again. Okay? So another way that you can turn an insulator into a conductor is you can add holes, which is the same thing as removing electrons. And then the holes can move around, and they are fundamental charge carriers that have a charge plus E. Okay? And so the excitations of this atomic insulator are the charge minus E electrons and the charge plus E holes. And that's something that's fundamental about this. Now, you might think this could be kind of useful. If you could add electrons and holes to an insulator in order to get them to be a conductor. That could be a useful thing. So in fact, a material that it's an insulator in which it's easy to add electrons and holes is called a semiconductor. Okay, and semiconductors are useful. Okay, and now, but real semiconductors, of course, are, this is kind of a cartoon picture. It seems oversimplified. You might think this is sort of the baby picture, right? Oversimplified, too simple to be true. Okay, real semiconductors are more complicated. So, for instance, silicon. Okay, so silicon is the semiconductor that is, in your computer, in the computer chips in your computer. Okay, it's the semiconductor that sort of forms the foundation for all the electronics technology that we use. Okay, so one of the great triumphs of quantum mechanics over the course of the 20th century was we developed the tools to understand the electronic properties of materials like silicon and many other materials, and we understand them in great detail. Okay, so silicon, for instance, has a particular arrangement of silicon atoms that form a crystal, and it looks kind of like this. So it has a particular arrangement, a crystalline arrangement of atoms, and it also has a particular structure to its electronic structure. Okay, now don't worry. I don't want you to worry about what all the wiggles on this graph mean. Okay, that's not important. The point that I want to get across about this, though, is that there are lots of details. We have very detailed information about the structure of this material. Okay, and it's that detailed understanding of that material that allows us to harness it in order to do all of the kinds of things that we can do with electronics technology. Okay, so real matter is kind of complicated. Okay, but this cartoon picture that I gave you, that's something it's kind of simple and you can understand. Okay, and I want to make a point, which is one of the is a deep and beautiful thing about physics. I want to make a point that there's a sense in which this cartoon picture is really right. Okay, and like silicon, it's still true that the fundamental excitations that carry electric charge are the charge minus E electrons and the charge plus E holes. That's still right. Okay, even in this complicated material. Okay, so there's something that this cartoon picture gets right. Okay, and so this sort of leads me to something which is, I think, very deep and beautiful about physics. Okay, and the way that I like to say it is that theoretical physics is kind of like an impressionist painting. Okay, so look at this painting. It's a beautiful, beautiful painting. But if you look at it too closely, if you look closely, it's all wrong, right? It's all a lot of dots of color. They're not even the right colors, right? And it's obviously much simpler than what's really going on. Okay, but if you step back from it and you look at it, there's a sense in which it gets it right. Okay. And so I would like to argue to you that theoretical physics is kind of the same way. Okay? And understanding the sense in which it gets it right is a deeply aesthetic experience. Okay? And I want to try to give you a little bit of that. Okay? And so in order to explain the sense in which this cartoon picture is getting right, I want to introduce a very interesting concept, which is the concept of topology. Okay, so now topology is a deep and beautiful branch of mathematics. Okay, and what it's about is it's about the study of objects that can be continuously deformed. And so what I want you to have in your mind is, imagine you have like clay. Okay, clay, you can mold it, you can squeeze it, you can stretch it, you can smoothly change the shape of what the clay is. Okay? And so the classic example for thinking about topology is to think about the sense in which a coffee cup is the same as a donut. Okay? So in topology, what we say is that objects are the same if you can continuously deform one into the other. Okay? And so look at this picture. Imagine you start with this is obviously a coffee cup. And what I'm going to do is I'm going to imagine smoothly changing it. So I make, at each step along the way, I don't change very much. I can imagine doing this continuously if it was made out of clay. Okay? And I make, these smooth changes, and at the end of the day, it becomes a donut. So you can sort of see the handle of the coffee cup has turned into the hole of the donut. Okay? So there's a sense in which the donut and the coffee cup are the same. Okay, and that's what topology is about. Okay? Now, that doesn't mean that everything is the same, though. Okay? Because imagine instead you had the surface of, you had a sphere, the surface of a sphere, like the surface of this orange. Okay? So I can imagine, smoothly deforming it. I could turn it into a pancake, for instance, if I just squeeze it down. Okay? But I can't turn it into a donut without poking a hole in it. Okay? And poking a hole, that's not something you can do smoothly, right? Because you have to go from not having the hole to having the pole at one instant, and that's a drastic change. Okay? And so the sphere and the donut are topologically different. Okay? And so what mathematicians like to do is they like to come up with some way of characterizing, what's the same about objects and what's different. Okay, and so in particular for this simple case of the sphere and the donut, there is what we call a topological invariance, something that can't change, which is basically the number of holes. Okay, and so a sphere has genus 0, whereas a donut has genus 1. Okay, and that genus is not something that can change continuously because it has to be an integer. It has to be 1, 0, 1, 2, or 3, and you can't smoothly change from 0 to 1. You have to do that discretely. All right. So you can ask the question. Okay, so this. Okay, but I want to say that it's this idea of smooth deformation is the sense in which this cartoon picture gets it right. Okay, so I want to have this principle and say that insulators are topologically equivalent if they can be deformed into one another smoothly while staying an insulator. Okay, and now most insulators are sort of kind of the same as this trivial cartoon-like insulator that I talked about. Okay, but this more complicated this silicon, okay, I want to argue can be smoothly deformed into this. So you can imagine you take your silicon atoms and you smoothly sort of, so they're locked in their crystal lattice. You can imagine smoothly making them further and further apart. Okay, and along the process of doing that, nothing drastic is going to stay an insulator. It's going to turn from this complicated, silicon insulator into this more atomic-like insulator. Okay, and so there's a sense in which these two insulators are the same. Okay, and in this insulator, the fundamental charge carriers are electrons and holes. So, for some purposes, it's simpler to think about this one. Okay, it's sort of like, if I want to think about, surfaces, the sphere is the simplest surface that doesn't have any holes in it. Okay, but that, it doesn't mean the surface has to be simple. It could be more complicated. So, Dave the octopus, he has a more complicated shape. But I don't think he has any holes in him. And so he has genus 0 also. So Dave the octopus's shape could be continuously deformed into a sphere. Now he's more complicated, But maybe there are things that you get right by thinking about the simpler case. Okay, and so that's the sense in which the simple cartoon picture of an insulator gets it right. Okay. Now, when you say it like this, though, this poses an interesting question, which is, so most insulators are, again, sort of topologically equivalent to this trivial atomic insulator, sort of like the sphere, right? But are there topological insulators which are like the donut, which you can't continuously deform into the trivial insulator? Okay? And so the remarkable answer to this question is that yes, and these topological insulating states are fascinating phases of matter with very interesting properties. Okay, and that's what I want to tell you about. Now, one thing I'll say is that the quantum theory of matter, that was developed a long time ago. There was 80 or 90 years ago. We've sort of had the tools at our disposal for understanding the electronic structure of materials. But people hadn't thought to ask the question of whether there could be sort of topologically distinct electronic phases. Okay? But once you ask that question, then that leads you along this path of inquiry, and there's amazing discoveries that have been made. And so that's the sort of these are the recent developments that have been going on. Okay, and so in order to introduce you to these topological electronic phases, what I want to do is I want to give you the simplest version I can think of. I always like to, in order to try to understand something, I always like to try to simplify it as much as I can, so I can have some simple picture that I can sort of get my head around. Okay, and the simplest version of this that I can think of is a one-dimensional polymer. Now, what a polymer is it's a chain of atoms. Okay, one after another. Okay, and so polyacetylene is a famous polymer, which is basically a chain of carbon atoms. And the carbon atoms then have some hydrogen. It's called a conducting polymer. Okay, but it's actually an insulator, it turns out. Okay, and it's an insulator in the following sense. So what polyacetylene wants to do is it wants to pair the neighboring atoms together. Okay, so that you have bonds between neighboring atoms which alternate between strong bonds and weak bonds. Strong, weak, strong, weak. Okay? And in doing so, that makes polyacetylene an insulator in the same sense where the sort of electrons are locked in place, they can't do anything. Okay? But the thing that's interesting about polyacetylene, though, is that there are two ways that you can do it. Okay? Because you can either pair them up going strong, weak, strong, weak, strong, weak. Or you can pair them up going weak, strong, weak, strong, weak, strong. Okay? And I want to argue to you that these two insulating states of polyacetylene are topologically distinct in the sense that I told you about. Okay? Now, the sort of impressionist picture that I want you to have in mind for what's going on with this. So I told you can understand an insulator by thinking that you have, your electrons are sort of stuck and bound to the atoms. Okay? So in this case, what we have is the electrons can sit, there are twice as many spaces for the electrons to sit than there are electrons. Okay? So in the A phase, I have these blue wells and the red wells. In the A phase, it's the blue wells that have the electrons in them. Okay? And in the B phase, it's the red wells that have the electrons in them. Okay? And so these are the two topologically distinct insulating phases. Okay? And so you can say, okay, well, so what? So we have these two phases. Who cares? Okay, what possible interesting consequences could come from that? Okay? So I want to show you a magic trick. Okay? So There's my magic trick. So, so I have my, this is my, my polymer. And I can, again, think of it that I have, electrons which are occupying every other space. And importantly, in this situation, I have my electrons, they have their charge, and then there's the protons that make up the atoms. They have the opposite charge. And it's important that they're exactly the right number of electrons to make it so that the total charge is zero. Okay? So everything is completely electrically neutral. There's just as many positive charges as there are negative charges. I'm only drawing the negative charges here, okay? But they're just the right number of positive charges to make this electrically neutral. So now what I'm going to do, I told you what is useful to do for insulators. It's useful to add electrons, okay? And if you add electrons, then maybe they can move around. Okay, so I'm going to add an electron to this insulator. There it is. Okay, so I added an electron. So now what I have is it's not completely electrically neutral anymore because there's an extra electron. Okay, so I have an exact charge of minus Benjamin Franklin minus E. Okay, and so this is what I have. So now I have a system that has exactly a charge minus E. So now I'm just going to move things around a little bit. Okay, so watch. So what I'm going to do is I'm going to take these electrons and I'm going to move them over like that. Oop, moved over. Okay. Now I'm going to do it again like that. Move them over. Okay, you sort of get the picture. I can keep doing that as much as I want. So now I want to ask the question, what happened to the electron that I added? Now, I know there's probably some of you wise guys in the audience here thinking, okay, there it is right there. I know you're thinking that, right? Okay, you're right, but think about it though, because you see, I told you that when I'm lining up every other positive charges. So in the middle here, I'm occupying every other site. There's no charge in the middle. The only place where there's any charge is where the electrons are kind of bunched together here. Okay? But there are two of them. Okay? I know I have a total charge of E, and these kind of look the same. So the electron that I added split in half. So this is amazing. That's against the rule. I told you can't split electrons in half. Somehow we got away with doing that here. Somehow we were able to make something that's impossible happen. Okay. So I think this is really cool. Okay. And so John Preskill. Okay. So John Preskill is a very famous theoretical physicist from Caltech, and but he also moonlights as a poet, and so he heard about this. Or something that was related to this when he listened to a lecture by Leon Balents. Leon Balents is another very distinguished physicist, actually a good friend of mine. And so Preskill was so inspired by this that he wrote a poem to commemorate it. And so this is the poem that he wrote. He said, "You have to admit it's legit. Electrons can split." Okay. So something very special is going on here, okay? You see, we started off in this insulator where the electrons were all occupying the blue spaces. This is what I call the A phase, okay? But then when I split the electron in part, what happened is in the middle, they're in the B phase, okay? And so what's happening here is that on the boundary between these two topologically distinct phases, we're somehow allowing the impossible to happen. Okay, we have exactly a charge E over 2. And it's not just approximately charged, it's exactly E over 2. Okay? And, and this E over 2, it's like a particle. It can move around just in the same way that, the electrons moved around or the holes moved around. This E over 2 is a particle, but it's a particle that has charge E over 2. Okay? And so this is the kind of thing that topological phases of matter can do. They can split the indivisible, okay, and allow these impossible things to happen. Now, this is the sort of simplest version of this, but there are many, many more examples of this kind of phenomenon. Okay, and so I want to tell you about some of these. So the first one I want to tell you about is sort of motivated by a problem, which is a problem with making very small electronics devices. And the problem is that in electrical conductors, the things that make up the electrical components inside your cell phone, there's lots of little wires and things where electric charge is flowing. And the problem is that in these electrical conductors, the flow of electric charge is kind of disorganized. Okay, and it's sort of like I don't know, when you come out of class at school and you're in this crowded hallway and you're trying to get to the next place and there's all these people you're bouncing into and it's hard to get where you're going, right? Well, that's sort of how electrons feel when they're trying to get through an electrical conductor. Okay, and so how might you go about trying to fix this problem? Well, one cue you might take is from how you try to fix problems with traffic, which is to make a divided highway, okay, where everybody's going the same direction, and you separate the ones that are going one way from the ones that are going the other way. Okay, so the question is, can we make this happen for the electrons in a conductor? Okay, and so what I want to show you is that using a topological phase of matter, this is possible. Okay, and in a sense, what I'm doing is I am splitting, the charges going one way from the charges going the other, and so this topological phases. It's the one that we understood first, and it's the one that we understand the best. Okay, and so this is a topological phase that's called the quantum Hall state. Okay, and it's a two-dimensional topological insulator. So what I mean by two-dimensional is that it's something which is in a plane. So it's like a piece of paper is two-dimensional. Okay, so it's something that's very thin, and so the electrons can only move around in the plane of the piece of paper. Okay, they can't move off. So in that sense, it's two-dimensional. And so what this quantum Hall state is that it's an insulator where on the inside, in the interior of this piece of paper, the electrons are sort of locked in place. They can't do anything. They're stuck. Okay, it's completely inert. Okay, but on the edge of this piece of paper, there is a one-way electrical conductor. Okay, and this it turns out that this two-dimensional conductor is characterized by an integer topological invariant, which is sort of like the genus, which counts the number of holes, in the donut and the sphere. Okay, there's a related topological invariant, and what that topological invariant tells you is the number of lanes that occur in this one-way electrical conductor on the boundary. Okay, and now this one-dimensional electrical conductor is an amazing thing. Okay, because if you were an electron, imagine you're an electron, right? And you go into one of these, you go into one of these states, then you have no choice but to go forward. That's the only thing you can do. Okay, you can't turn around because there's no place to turn around to. In order to turn around, you'd need to go across to the other side, and that's far away. Okay, it's like there are no cars turning around on the interstate, right? Okay, so it's sort of like that for the electrons. Okay, so another thing that is interesting, if you could just have one of these by itself, let's imagine you could just have a one-dimensional thing, which is just one of these one-way things by itself. If you could have one of those by itself, that would really be amazing. Okay, you know what you could do if you could have one of those by itself? You could take the entrance and put it inside your refrigerator and have the exit outside your refrigerator. And then you'd be able to run your refrigerator without having to plug it in. Right? Because it would take the heat from the inside and take it to the outside. Okay, keeping it cold on the inside. And if you could do that, you'd be rich, right? You could solve all the world's energy problems. You know, you could make a perpetual motion machine. Okay. There's a catch, though. If anybody tells you that they can do that, then that would be fake news. Okay. You see, because it's impossible. Okay, so having one of these by itself violates deep principles of physics. Okay, so it's impossible to have one of these by itself, but it just in the same way that it's impossible to have half of an electron by itself. Okay, but it is possible to have it on the boundary of this topological phase. Okay. Now, of course, so you can think, just like with the in the Polyacetylene thing, what I did is I split the electron in half. Okay, and I can't have one half without also having the other half somewhere else. Okay. Likewise, here what I've done is I've split an electrical conductor in half with half of it going this way and half of it going this way. So you can't have this without also having this. Okay, and so if this went into your refrigerator, then this would also. Okay, and that's the reason it doesn't work. Okay, so but you can have this impossible thing, on this boundary, and the thing is that it has to be there. You see, you can't cut this off, right? Because if you cut it off, then you'd have this impossible thing by itself. Right? So it has to be there. You can't get rid of it. Okay. And now I'm actually telling this story a little bit backwards. Sort of sitting in a room thinking about donuts and coffee cups and things like that. It was actually discovered in the laboratory. This was one of the great discoveries of the sort of later part of the 20th century, the discovery of the quantized Hall effect. And this is sort of multiple Nobel Prize physics. Okay, and so what so it started with von Klitzing in the 1980s, and what he was interested in at the time is he was interested in developing semiconductor technology. He was studying the semiconductors that now go into your cell phone. Okay, and he was sort of trying to characterize their electronic properties. And what he discovered is that when he measured the electrical resistance in a big electromagnet, it turned out that this electrical resistance had these very flat steps in it, and the value of the resistance on these steps turned out to be related to an integer multiple of this combination of fundamental constants. So this, don't worry about this. This is Planck's constant, and this is the charge of the electron. But the important thing here is that this fundamental constant is a fundamental constant of nature, and this n here is an integer. And the amazing thing is that this integer, by measuring the value of this resistance, you can measure this integer to be an integer to 1 part in a billion. So it's like 1.00000 with 9 zeros. Okay. Another way of saying it is that by measuring this resistance, you can measure the value of these fundamental constants to 9 digits of accuracy. So in fact, this is how we understand what the fundamental constants are, by doing this kind of experiment. Okay, and so this is amazing. I mean, so at the time, people thought, how could it possibly be? You do a measurement on a device that looks like this. It looks like a piece of crap, right? I mean, there's all these little gobs of solder. It's not a perfect sample. It's all dirty, right? But somehow when you measure the electrical resistance of it, you get a perfect electrical conductance. So how could that be? So at the time, people thought, well, who ordered that? And so this was the beginning of that motivated, sort of geniuses in theoretical physics, people like Bob Laughlin, David Thales, and others, to think deeply about what's going on with the electronic properties. And they realized that what is going on here is that this integer is actually a topological invariant, something that can't change even if you mess it up. Okay? And so this was the beginning of the quantum Hall effect. Now, you might think that, having these one-way edge conductors, that could be pretty good, right? Maybe you could put them in your computer and that would organize the flow of electrons. Now, the problem is that in order to get this to go, you need to have a big electromagnet. And so this is a magnetic field. In order to get 8 Tesla of magnetic field, you have to have a pretty big magnet, okay? And you don't want to have to carry that around in your cell phone, okay? That's not practical, okay? So you can ask the question, well, could you get this to go somehow without having the big magnet? And that's a hard problem, something people are trying to solve. Okay, we haven't completely solved it yet. But one way of possibly being able to do that is to use another kind of topological phase. Okay, and this is one that was discovered more recently, which is called a topological insulator. And so let me tell you about a topological insulator. Okay, topological insulator is I like to say it's sort of like a chocolate treat that is wrapped in tinfoil, okay? In the following sense, that it's an insulator on the inside, okay? The chocolate is like an insulator, but it's an electrical conductor on its surface, the tinfoil, okay? But actually, it's a little bit misleading what I'm doing here, because it would be a very frustrating chocolate treat, because if you tried to cut it open, you can't unwrap it. It would still be wrapped. Okay? So this conducting surface is one of these things that's impossible to have by itself. Okay? It's impossible in the same way that half an electron is impossible, or this one-way electrical conductor is impossible by itself. This conducting surface is impossible in the same way, and that means you can't get rid of it. Okay, you can't peel it off, because if you peeled off, then you'd have it by itself. Okay, and so this conducting surface, it has a very specific property. Okay, and what we in the lingo of our field, what we do is we say it has a single Dirac cone. Now, I don't want to try to explain to you what that means, okay? But there's a very specific property that this impossible surface state has, okay? And so this is a prediction, and unlike the quantum Hall effect, which was sort of discovered serendipitously in the laboratory, and then that inspired people to think deeply about it and come up with some understanding. Actually, the topological insulators were sort of discovered backwards, the way it doesn't, the experiment first, that's the way things usually happen in physics. Okay? But the topological insulators were actually discovered sort of more by, it started off with sort of pure thought. Okay? And, I played a role in that, but thinking about what are the possibilities for what kind of topological electronic structures that materials can have, okay? And that led to theoretical predictions of materials to look at and to try to probe and see what would happen. And it was really, so the pure thought, that's nice. A material called bismuth selenide, and it's a material that has a particular crystal structure and a particular detailed electronic structure, which one can do some calculations to understand. And then one needs to do an experiment in order to look at, once you have this crystal, then you need to sort of figure out how to look at it in order to tell what it is. And so it turns out there's a tool called photo emission spectroscopy, which basically is like taking a fancy picture of the crystal. And this is demonstrates the presence of this Dirac cone that I told you about. Okay, and so this demonstrates that this surface has this impossible conducting surface. Okay, and so this is a topological insulator. Okay, now I want to, in the brief time that I have left, I want to tell you about one more topological phase, which is really cool, and it's also motivated by a problem. Okay, and the problem is something that we really would like to be able to do, and this may happen in your lifetime. I'm not sure. Okay, we'd really like to make a quantum computer. Okay, let me try to tell you why a quantum computer would be something that would be nice to have. So an ordinary computer, the usual, computer. What it does is it performs operations on ordinary numbers, which are stored as bits. So a bit is a 0 or a 1. You can sort of think of it as like a switch that's either on or off. And if you have n bits, then you can encode an n-digit binary number. So if any number you can write in its binary base 2 form, and it's just a bunch of 1s and 0s. So like 5 is 1, 0, 1. It's 4 plus 1. Okay? And so what an ordinary computer does is it takes a bunch of bits and then it does some operation and spits out the answer. Okay, here it just adds 2 to it. Okay, so what a quantum computer is, or what quantum information is so this is something that quantum mechanics allows you to do. Now, don't ask me to explain to you why this is true. Okay. Because I don't understand why it's true. Okay? Nobody understands why. So we understand the rules of quantum mechanics, but we actually don't be on or off. What quantum mechanics allows is that it can be on or off, or it can be both at the same time. Okay? And so this phenomena, which is called quantum superposition, having it be both at the same time, is a mysterious feature that quantum mechanics has. And we know it's right, okay, even though we don't quite understand what it means. Now think about what you could do with this, though, because if I have a single bit, I can store both 0 and 1 at the same time, both numbers. If I have n of these quantum bits, n of these qubits, then I can have all of the n-digit binary numbers at the same time. Okay? So now what a quantum computer is it's a device that does an operation on these states. And so think about what would happen if I, so quantum computer, I can have it, add to. But now if I send this state in, I'm sending in all of the n-digit binary numbers, and I do one operation, and I get all of the answers. Okay? So if I wanted to get all the answers in a classical computer, I'd need to do it over and over again 2 to the n times. Okay? And so I hope you can see that this idea allows a quantum computer to be much more powerful than a classical computer. Now, if you think this is too good to be true, you're right. It's actually not this good. Okay, there are subtleties about this. But it is true that there are classes of problems that a quantum computer can solve much more quickly than a classical computer. And so that's a tremendous motivator to get us to figure out how to make a quantum computer. Now the problem is it's really hard. And so making a quantum computer is one of the grand technological challenges of the present century. Okay, and maybe some of you will grow up and be the people who make this happen. I mean, it's not going to be, I'm too old. Okay, so but here's the problem. Okay, so the problem is that quantum information is very fragile, because if you try to measure it, you don't. If you have this thing which is either 0 or 1. If you try to look and see which one it is, you don't see that it's the combination of the two. You see it's one or the other, and it's sort of like flipping a coin as to which one you get. Okay, and moreover, once you've looked at it, then it's not in this combination anymore. Okay? So what that means is in order to measure a state, you have to kill it. Okay? And so this is a fundamental obstacle that quantum mechanics gives us. Okay. Now, and as a matter of practice, the question is let's suppose you have this quantum computer. How do you keep it from accidentally measuring itself? Okay. Now, it doesn't have to be a person that looks at it. It could be the sort of rest of the computer sort of effectively interacting with your qubit and destroying the quantum information. Okay. And so this is a big problem. Okay. And it's this difficulty which is why we don't have a quantum computer at this point, okay, that can do anything useful. But it's a great challenge that's out there, and the person who makes it work is going to get very famous. Okay, and so there are a number of approaches for how you might be able to do this. One approach is to have your qubits and just have them be really, really isolated from everything else, so that nothing else is interacting with it. And that's a possible approach. What I want to tell you about is another approach which uses a topological phase of matter. Okay? And so here's the idea, which I can tell you quickly, is, I told you that topological phases of matter allow you to split the indivisible. Well, a qubit, this switch, that's a sort of, you think that's an indivisible object, but there exists a topological phase, and it's called a topological superconductor. Now, I'm not going to try to tell you what a superconductor is, let alone what a topological superconductor is. But let me tell you that the way we think about it is very similar to the way we think about insulators and this polyacetylene thing. It's very similar. What a topological superconductor allows you to do is to split a qubit in half. Okay, so that half of it is over at one end of a one-dimensional system, and half of it is at the end. And we call this half of a qubit. We call it a Majorana end state. So that's the name we associate with it. And so the beauty of this, though, is that this qubit, encodes one bit of quantum information. It could be 0 or 1 or both of them at the same time. Okay, but if you try to look at just one of the ends, you're only looking at half of it. It's impossible to measure what the state is. Okay, and because it's impossible to measure it doing a local measurement, that means that this quantum information stored non-locally in these two qubits, which are far away from each other, that information is topologically protected. Okay, so that's one possible way of keeping your quantum computer from accidentally measuring itself. Okay, and so now this of course is a big so how can you make this happen? Okay, so even making a one-dimensional topological superconductor, that is a hard problem as well. And this is a problem which we're not completely there yet, but there's been tantalizing progress. Okay, and so it turns out that certain kind of semiconductors, if you combine them with certain kinds of superconductors, you can make something which looks like it has one of these Majorana end states. Okay, now people are still fighting about whether this. It's kind of hard to see here. I guess there's a little peak in the data here. People are still arguing about whether this peak means that it's a topological superconductor or not, but it's looking pretty good. Okay. Now, of course, it remains to demonstrate the fact that these Majorana states can store and possibly manipulate quantum information. That's a problem for the future. But this is a very exciting time to be studying things because there's a lot of progress, and I think there's a lot of things that are going to keep happening. Okay. And so let me. I think I'm just about finished. And so let me I want to close. I want to leave you with a thought when I close, which is so it's this idea that there are two things you can shoot for in physics. You can try to understand what the sort of fundamental building blocks of matter are, what it's made out of, and what the rules governing those fundamental building blocks are. So that's one very productive line that you can take. But there's another direction you can go, which is, given those building blocks, what can you make out of it? Okay, what can matter do? Okay, and that, you see, things can emerge which were not obviously present in your fundamental building blocks. How do you get this half of an electron? That wasn't one of your building blocks. And so in order to understand these kinds of things, one needs to develop sort of organizing principles for understanding what is possible. Okay, and so the analogy I want to give you is to think about classical mechanics. So if you take a first course in physics, you learn about Newton's laws. Okay, and so Newton, back in the 1600s, he basically got it all. Newton's laws. He wrote it down. He solved all of classical mechanics by writing down F equals ma. Okay, and everything else follows from that. But so there's a sense in which he understood the sort of fundamental rules, but it was only 200 years later that people came to appreciate that energy as an organizing principle for thinking about how to think about classical mechanics is an important idea. Okay, and of course now we teach energy in the third week of beginning physics. Okay, and it forms a foundation for not just classical mechanics but all branches of physics. Okay. So I want to say that so the just like Newton, the sort of fundamental rules of quantum mechanics, those are sort of written down at the beginning, early part of the 20th century. We know those, just like we knew Newton's laws. Okay, quantum matter are still being uncovered, and there have been lots of surprises and things that you wouldn't have thought of before. Okay, and so this makes it a very exciting time to be a physicist, and because there are many things that are happening, and so matter can arrange itself in the most ingenious ways. So, thank you.
Well, thank you very much, sir. That was a fantastic lecture. Okay, do you have some questions, maybe, or comments? Yes.
I just had a question about when you were talking about negative E/2. Were you saying that the electron itself was being divided, or is it the probability distribution?
Yeah. Okay. Good. So very good. So no, to neither of those. You see. So actually, this E/2. Everything is made. I'm not splitting any particular electron in half. Okay. What is happening is I have lots of electrons. Okay, and it's the collective behavior of all of the electrons that form this lump of charge that has a charge E/2. So if you think about this, so you could say, I know there's exactly a charge E/2 sort of in this region, but it's not exactly these two. These two electrons, of course, have charge 2, but they're compensated by the background. But I know that if I separate this, far away, then in that region, there's got to be a charge E/2. And so that charge is made out of kind of all the electrons. Okay, but they're sort of bunched together a little bit. When I started, I know that I had exactly one extra electron that has exactly a charge E, and so and all I did was was separate them, and so this charge E/2 is something that emerges out of the collective behavior of all of the electrons. So it's not that I'm splitting a particular electron in two. It's that somehow this charge E/2 particle emerges out of the collective behavior of all of the particles. Very good question, though. Thank you.
Yes, please.
I'm curious about what kind of topological invariance you're considering.
Yeah. Okay. So So the one that was developed first was the topological invariant for the quantum Hall effect. So this is the one that described this topological invariant. It's an integer, and it has a name. It is called the Chern number. That's what mathematicians call it. And actually, in the Simons Center here, so the Chern and Simons were very famous mathematicians who developed some of these ideas. And of course, Jim Simons is the Simons of the Simons Foundation and the Simons Center. So that's that. So the topological invariant that characterizes the two-dimensional topological insulator is the Chern number, and it's very much like the genus. Okay, it's like the genus in a space where you use complex numbers. Okay, so it's a little bit harder to think about, but the sort of mathematical formulation of the Chern number is quite similar to the mathematical formulation of the genus that distinguishes a sphere from a donut. Now, there's also a topological invariant that characterizes this three-dimensional topological insulator. And so this is a different kind of topological invariant. Instead of being an integer, which can be 0, 1, 2, -1, any integer, this topological invariant only has two possible values. Okay, it can be 0 or 1. And so we give that a name. We call it a Z2 topological invariant because Z2 is the group that has two elements, 0 and 1. Okay, and so this is a topological invariant that was developed somewhat later. Okay, and so that was one of the contributions that I gave this field, which is introducing the Z2 topological invariant. Yeah.
Yes.
Quantum computer properly function wouldn't need a topological superconductor?
Well, if you're using the architecture that I'm suggesting here, so for this kind of method for storing the quantum bits, then you would. But there are other possible architectures that may be may work better than this. Okay, so one, so the question is how do you store the quantum bits? Okay, and so one way you can imagine storing the quantum bits is to use the spin of an electron. Okay, which has two states it can be in, or you could use some kind of there are also some kind of superconducting devices that have two states they could be in, and so those are things where if you had your qubit, you have to work very hard to keep them to be very isolated from everything else. Okay, and so but you don't need a topological superconductor in order to do it. Okay, so for this proposal where we're splitting the qubit in half and using that as the way of protecting it, then for that you do need a topological superconductor. But my guess is that if we're able to make a quantum computer, I'm not so sure it's going to be this architecture that is the most practical. Maybe some combination. This may have some features that make it useful for some parts of it. There's a big engineering problem of finding the way that works the best.
Okay. So would this be the only way to split the qubit in half?
Yeah. Yeah, I think in order to split the qubit in half, you need some sort of topological phase. Now, I will say that this story of the topological superconductor splitting the qubit in half, that there are more kinds of versions of that use even more exotic kinds of topological phases, which in principle are possible, but are a little bit further from reality at this point. We have theoretical ideas that suggest that they should be possible, but we don't quite know how to make them happen. Okay, and so but maybe there will be some breakthroughs in our understanding of materials that will allow those to happen as well. So so there's a lot of this is a very active and very current field in physics right now. There's a lot going on.
questions or comments? Okay, well, let's thank Charles again for a great talk.
Thank you.